Okay. Well, I work mainly on the rather messy aspects of the later universe, and so I think one should acclaim what Planck has done in finding 70,000 discrete sources, more than 1,000 Sunyaev-Zellervis clusters, and a great deal about our galaxy and the interstellar medium. That's great. But I wanted to talk now about 4 of the basic numbers from the early universe. The fluctuation amplitude, the vacuum energy density, and the 2 important numbers, the baryon-photon ratio and the baryon-dark matter ratio, which are well pinned down and are crucial for our universe. Now, what we really like is to understand all these in terms of physics tested in other ways, just as we understand the helium abundance of the universe and have done for nearly 50 years. And clearly, most of these 4 numbers depend on physics which is not well known. I think the one clear prediction is, of course, the tilt in the spectrum. That's a wonderful prediction of inflation. But I think it's important to note that the actual basic amplitude, the fact that in order of magnitude the fluctuation of 10 to the minus 5, is, I think, not yet predicted. And therefore it's interesting to ask why is that number so important, and what would the universe be like if it were different? Now, people may think I'm going to talk about anthropic things, and that makes many foam at the mouth. So I won't do that, but I will talk about what you might call counterfactual universes. And this is just like historians or biologists may want to ask what would happen if the dinosaurs weren't wiped out. It would be interesting to explore that, and more recent historians might want to know what would happen if the Brits had joined the euro or something like that. So in the same spirit, I want to tell you why this number 10 to the minus 5 is so important. If you call it Q, then this number is roughly the fluctuation amplitude, and the maximum nonlinear scale in the universe is Q to the 1/2 times the Hubble scale. This is about 10 megaparsecs in our universe, and the binding energy of bound systems, clusters of galaxies, is Q times their mass. 10 to the minus 5, their velocity is 10 to the minus 2.5 c, 1,000 kilometers per second. And it takes a factor Q in expansion time at least for fluctuations to go non-linear. And we're familiar with this picture. Now, let's just ask, what would the universe be like if Q were different? Of course, if it was essentially 0, we'd still be an empty universe. But if Q was 10 to the minus 6, then we'd have what I call an anemic universe. Galaxies would form rather later. They'd be more loosely bound. We wouldn't have anything like clusters. This is a universe we could maybe just about live in, and of course, even a small lambda would prevent even that from forming. On the other hand, let's go the other way. Let's suppose we had a universe where Q was 10 to the minus 4, 10 times bigger than it actually is. This would actually be a rather interesting universe to live in, because the scale of clusters would be a lot bigger, and what would happen, for instance, is that objects the size of the Coma cluster would collapse at a redshift of 10 when Compton cooling was important, and you'd have huge disk galaxies forming at a redshift of 10 of about 10 to the 14 solar masses. This would be a rather interesting universe. No anthropic selection against that. If you go still further, 10 to the minus 3, then perhaps things get more difficult, because then you get huge black holes turning around when the Thomson depth of the universe was large, and you might not get any galaxies. So this is why the value of Q is so crucial, and I think I'm right in saying that that value of Q, which depends essentially on the energy at which inflation occurs, plus other numerical factors, is not yet pinned down. We don't yet know a priori why we should live in a universe which has a sort of degree of roughness that ours actually does. And this is a challenge, obviously, to try and understand that amplitude. The next challenge for the inflation people. And the vacuum energy lambda, I won't say any more about that. We don't know if it's constant, and this if I were to bet, I think this is the challenge that will be furthest in the future to meet, and maybe never. Just a word. Oh yes, I wanted to mention this. If we consider two parameters, the fluctuation amplitude along the bottom, and there's no scale here, but this is lambda. Then we're familiar with the idea that for our universe, we're q 10 minus 5, then our actual universe has a lambda which is about a tenth of the maximum which is allowed before galaxy formation is inhibited. It's interesting to note that if q were 10 times higher, then lambda would be allowed to be 1,000 times higher. So there is in fact there is in fact this fairly large anthropically allowed area of possible universes with different values of the fluctuation amplitude and different limiting values for lambda. Well, just a word about the last two numbers. The baryon-photon ratio, I think most people believe this is related to CP violation, etc. Lots of models. People are not surprised it's a rather small number, of about order of 10 to the minus 9, but one suspects that it's going to be pinned down at some stage. The baryon dark matter ratio, this again is going to depend on finding out what the dark matter is. So I think if I was to make bets, I would bet that the first number to be pinned down would be the baryon, would be the dark matter, and then it might be a bit longer to pin down the baryon density, and the others harder still. And I think let's not forget that there's about 20 powers of 10 in time between the inflationary era and the earliest era where the energies could be probed by the LHC, and a lot of physics can happen in that domain. And so let me finish with that.
Okay, so now I'd like to invite questions for the panelists. Yeah.
Like many people here, I'm just amazed by the big success we have. But still, I would like to look on. And that is the question about the standard model and how it works at a scale of galaxies and satellites and also inside the galaxy. And the smaller the scale we get, the more I see the problems growing. But I would like to pose the question at the panel.
Yes. Well, I think you're quite right in saying that once things get nonlinear, as they are on all scales below 8 megaparsecs, roughly speaking, then things get harder. And the complexity grows as we get to the scale of galaxies, down to the scale of stars and planets, and down to the scale of human beings. So as the scale goes down, the complexity goes up. And I think that is the challenge. I think it's going to be harder to understand planetary systems than stellar systems, which is in turn harder than to understand clusters of galaxies.